Today we have a very interesting presentation from Harry Ricker here, and it's on resolving Faraday's paradox, and we have the interrogation at the end, because I think Harry's thesis will be that resolving, the paradox, look at all the information, no such thing, we haven't resolved it.
I'm going to talk about this paper that came out in October. I think it was the first week in October or so that was published. And there's a blurb. Unfortunately, I can't show you the blurb that came out. So there was an announcement that appeared in a science publication, and that was titled Resolving Faraday's Paradox. The paper doesn't have that title exactly. It's got a different title. It talks about doing experiments. Okay, and so this is kind of interesting because this is a long-standing problem. What did they do, and did they accomplish this goal? And if you don't know what Faraday's paradox is, that's kind of a buzzword for the problem of unipolar induction, which was a long-standing problem uncovered by Faraday. And he did experiments that didn't quite fit his theory. Now, my claim is that there really isn't a paradox. There's just only a lot of confusion. So what they are doing is they've sort of called this confusion that they've created over 150 years or however long it's been since Faraday did his original experiments. And all that they've done really basically is create more confusion by arguing amongst themselves and saying my theory is better than this theory, et cetera, et cetera. So what we have is a lot of confusion created by people coming up with theories and based on assumptions that weren't necessarily valid. Now, my assertion is, and if you read the literature, you'll find that a lot of people say that this confusion doesn't invalidate the Faraday flux law. And I was gonna, if I could share screen here, I'd show you some papers where they say this. And the problem comes about because a lot of people want to use the Lorentz force law acting on electrons inside the wires. So the magnetic field is supposed to exert a force on electrons inside of the wires. And the problem is that they can't define what the velocity is to use in this Lorentz force law equation. And when you use this velocity relative to the magnetic field, it doesn't work correctly. You don't get the right answer, and you get what would be called a paradox. Now, the reason is kind of basically the whole crux of this problem. Now, my personal opinion is that the reason that this isn't working very well is because they're using the velocity of the magnetic field, and they should be using the velocity of the circuit components when you calculate the velocity. So it's the motion of the physical circuit itself relative to other parts of the circuit that actually is to be used in the V, not the velocity relative to the magnetic field. Now we're at the presentation that I've been talking from. This is the second slide. Now, one of the reasons that you can say that the velocity that we're going to use in the calculation is the velocity of the circuit motion is because we have sliding contacts. So when we have a sliding contact, we know that there's a movement, a relative motion of the circuit. So we have to have a sliding contact. Now, the other thing that we deduce from the measurements is that we have to have a magnetic field in the part of the circuit that's moving. Now, this turns out to be one of the points of confusion that I'll talk about later. And it turns out that when you do these experiments, and we're going to see this in the results that these guys got, doesn't really matter whether the magnet is moving or not. Doesn't matter whether the magnet is rotating or not rotating. And in these experiments, we're dealing with rotational motion. And it's the relative motion of the different parts of the circuit that produces the EMF. Now then, there's this other problem that we have, is that the seat of the EMF cannot be isolated to a single circuit element. And this is kind of a tricky thing, because people have tried to put voltmeters onto the magnet or the circuit that's spinning, part of the circuit that's spinning, and they don't measure any EMF. And this kind of confuses people. So this issue of where is the EMF being generated is one of the controversial issues that makes for confusion. So we have to be a little bit careful about talking about what produces the EMF and where it's coming from. Now, this whole thing has to do with this problem of unipolar induction, and that comes from Weber's work, who did some experiments after Faraday. And it says that in the unipolar part means we're only dealing with one pole of the magnet. And this is kind of where things get a little bit confusing, in that if you have more than one action of the pole, so in other words, if one pole acts twice, or you get an action from the south pole and the north pole, they kind of cancel each other out. So this is one of the areas of confusion. Okay, now the paradox in the unipolar induction is that when we use this Lorentz force law, the voltage that you get is zero. So in other words, the voltage should be produced, but because the magnetic field is rotating, but there's no voltage when the magnetic field is rotating. And that happens if the disk or the wire is stationary. So if the disk or the wire is stationary and the magnetic field is rotating, you get no voltage. But according to this Lorentz force law, you should get voltage, but you don't. Then you have using the Lorentz force law, voltage is, you only get a voltage now, this is what's interesting, when two different parts of the circuit are moving. So, and this can happen when the magnet is rotating synchronously with the disk. Here's the illustration of, this is the resolving Faraday's paradox. This is the announcement that of these experiments that they did. And this kind of illustrates the problem that they're going to investigate. You have this magnet that's spinning. You notice there's an arrow here showing that it's spinning. Then you have a disk, okay, and it's spinning. And then they have a circuit here to measure the voltage, okay. And this is the standard Faraday disk arrangement, but we'll find out they don't actually use discs necessarily in the experiments. They use basically wires to substitute for the disc, but they have a spinning device. Now the assemblage, here's the table that they produce. They say that their theory is consistent with Weber's theory of electrodynamics. Whether the field of the magnetic field is moving, they say is stationary. If the magnetic field is stationary, the magnetic field is moving. Okay, and they say, well, all of these theories are confirmed by the experiments, which is kind of confusing. You think, why would you want to confirm all the theories? You would want to eliminate theories, you would think, according to the scientific method. So this is sort of something kind of confusing and suspicious about what they did. Okay, let's go. Is everybody kind of, you know, I was just going over this a little quickly here.
What does omega mean?
That means that the device is moving. It says DA means that it's rotating. Meta means that it's, you know, their notation. Probably what, this is kind of a truth table. These truth tables are kind of useful in analyzing this data. There should have been a 1 here where it says omega, 1 meaning that it's true that it's moving. You understand what I'm saying?
No.
Omega means that the disk DA or the wire DA is moving.
Oh, okay.
0 means it's stationary. 1 means that there's a voltage detected, or in this table, they predict the voltage would be detected. 0 means there's no voltage detected. And this would turn out to be another problem. Okay. So now let's go back to the presentation here. And I guess we got a few minutes. Now, we're down here to this third point, which when Faraday did these experiments, he ran into this problem of it didn't really fit his theory. And he came up with, and he hypothesized that the field of the magnet is stationary and is not rotating when the magnet is rotating. And that sort of presents this problem that this doesn't really make sense as a physical hypothesis. How can you say that the magnetic field doesn't move when the magnet is moving? And that's created a problem. And that's really the first issue that comes up with this controversy. Now, while you might want to call this be Faraday's mistake, okay? Faraday had this flux cutting rule that he came up with. And what he did was he took a wire and that was connected to a galvanometer, and he moved this wire around in the pole of near the pole of a magnet, big magnet, he had a big horseshoe magnet, I think, and moved this wire across the pole of the magnet. And when he did that, he got a response in the galvanometer that indicated a current was created. And so he came up with this idea that when the wire passes across the magnetic lines of force, a force was created inside the wire, so to speak, that created the current that was measured by the galvanometer. And that sort of shows up as Faraday's flux cutting rule. So what Faraday is saying, when I move across the lines of magnetic force, I'm going to get an EMF. Now, what happened is that this particular hypothesis doesn't work when you have the unipolar induction, or the machine where a disk is rotating or moving in a magnetic field, because if you're supposedly the disk is passing across the magnetic lines of force, but when he tried to make his theory of flux cutting apply to this, it didn't work. Okay, he got this contradiction, which is now called Faraday's paradox. And so he couldn't resolve that unless he came up with this hypothesis that the field is stationary. So his flux cutting rule didn't work well for this unipolar induction case. Now, that had to do with, in the unipolar induction case, the magnet can be spinning. In other words, the magnet's spinning, there's no disk. So you go from another experiment where you have a spinning disk in a magnetic field, and then in the unipolar induction experiment, the magnet itself, a cylindrical magnet, is spinning, and you can measure an EMF between the pole of the magnet, or the end of the cylinder, and the middle of the magnet, and that will produce an EMF. And this presents a rather confusing case, because the magnetic field is moving, so it's not moving relative to the circuit inside the magnet. It's kind of a confusing thing. But the flux cutting rule didn't really apply in this case, and so that's where this paradox arises with respect to unipolar induction. Now, after he'd done a bunch of experiments, he realized his rule didn't really work, but it would work if he assumed the magnetic field was stationary instead of spinning with the magnet. And that's really what the paradox is. Okay. And so what's the bottom line here? These experiments that were done by Faraday, they were done in 1852. His original experiments were in the early 1830s, and he came back and did more experiments in 1852, and that's when he enunciated that the field is stationary and doesn't move. So this is a problem that's been around for quite a while, over 100 years, 150 years, something like that. So we got a problem. Why can't we resolve this? Okay, so supposedly these people who did these experiments that were released in October, you would have expected, a problem that hasn't been solved in 150 years. This is a big problem of science. You would expect that they would have been able to solve this problem. But what they did was they said, well, we have 3 theories that can all fit the experiments. That's not really solving a problem. It's, not resolving anything at all. But I'm going to explain a little bit later. Okay, so when they did these experiments, they said that the stationary field, the moving field, and the Weber theory all basically satisfy the measurements that they made. So it's kind of hard to understand how you resolving a problem in science if any theory can fit the results. Okay, so the procedure that they're using when you do a scientific method is you make predictions. This is the procedure that they used. They make predictions based on the theory, and then you do an experiment, okay? And then you compare the experiment results to your predictions of your theory. But they got 3 theories. They made predictions with 3 different theories, and they all gave the same results, okay? So this seems to me to be not really doing things very well. And we'll find out that what they did was they didn't really address the problem of the paradox. They sort of didn't really structure the experiments properly. But the real issue was, and this is my thesis, the real issue was that they wanted to make the Weber theory consistent with the experimental results. So in other words, the Weber theory could be able to claim that it had some success in making valid predictions. But the difficulty was that the other theories, they didn't really eliminate other theories in favor of the Weber theory being the only theory that made the correct predictions. They just made it so the Weber theory is an additional theory that gives the correct predictions. So that's not really eliminating, a theory. It's not really, it's just increasing the number of theories that can be, that you can claim are valid theories, rather than reducing the number of theories. I mean, presumably, the ideal way you want to do this would be you'd want to reduce the number of competing theories, not increase the number of competing theories. Okay. What people have done in the past is they have tried to do this eliminating of the theories or reduce the number of possibilities by shielding part of the circuit or shielding the closing wire. So if you recall this sharing process is a little more difficult than okay, so we're back to our diagram of our machine. What they're saying is this part of the circuit here with the voltmeter in it, You see what I'm saying? Showing here, moving it around. Where
Yes, 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 yes.
Okay, the idea is that this particular part of the circuit, it's subject to the magnetic field. So in other words, the magnetic field from the magnet passes through this part of the circuit. Okay, and so that creates this problem that you're not really eliminating some of the possible theories. You're basically, all the theories can explain it. And so what people have done is they've tried to shield this part of the circuit so there's no magnetic field there. Okay, but that's not what they did in these experiments. They actually allowed the magnetic field to be part of this circuit. So in essence, they kind of did the experiments wrong. So instead of shielding, this part of it should have been shielded, and they didn't do that. So they didn't really test the unipolar induction case. That's really the basic bottom line. And now, the other thing here too that I want to, if you do the closing, if you shield the closing wire, you'll get the same results that Faraday got. Now, this is kind of an interesting point, and that is Faraday went to a lot of trouble to make sure that there wasn't any magnetic field induced in the wires that connected to his galvanometer. And when he made sure that there wasn't any magnetic field getting involved, flux lines crossing that part of the circuit, that was when he came to the conclusion that the magnetic field was stationary. So he had already done this. But what happens is that people have been repeating this experiment over and over again, not realizing that Faraday had already done it. That's kind of a big, that has to do with the fact that people didn't really look that closely at what Faraday had written in his book. Okay, so what they did in the experiment that we're talking about, where they claimed to have resolved the paradox, they didn't shield the closing wire. Okay, so they didn't really test Faraday's paradox. Now here's the problem now. All right, now I looked at this, and part of the controversy has to do with people say, well, if I have a bar magnet and I'm spinning it such that spinning its axis so that the north poles and the south poles are spinning around in a circle, the magnetic field is following the motion of the magnet. So how can you say that the magnetic field doesn't move with the magnet? It's stationary. Certainly it's not stationary in that case. One of the things that I did was I found on the internet, there's an interesting video where they rotate a magnet, a circular cylindrical magnet, and they use a ferro fluid. I don't know if you're familiar with ferro fluid, but it's a fluid that responds to magnetic field, and you can sort of see the field lines in the fluid. And you can see as the magnet rotates that the fluid is moving around and responding to the rotation of the magnet. So that sort of, in my mind, sort of takes away the non-physical hypothesis that the magnetic field lines don't rotate when the magnet is rotating. So, now we got a lot of confusion going here. The test that these people didn't really test the paradoxical aspect of the Faraday paradox. They tested something different and said that, well, all of our theories explain this, the three theories: the stationary field theory, the moving field theory, and the recovery theory.
If the magnet is symmetrical along the axis of rotation, why wouldn't you expect that the resulting field would be rather unchanged or have minimal change?
Well, yeah, it's sort of a surprising thing that people actually haven't thought about that. And obviously that's part of the solution. What happens is that when you spin the magnet, there really isn't any change in the flux, okay, as a result of spinning the magnet. So what you have is you have a constant flux produced by the magnet, whether the magnet's spinning or not spinning. What changes the flux, what causes the EMF to change, is the movement of the circuit. It's the movement of the electrical path in the circuit. It's when that part is changing that you get an EMF.
Thanks for the clarification.
Does that help you? This is really a key point, and there's a lot. So,
Well, aside from manufacturing abnormalities in the distribution of the magnetic components, I would expect that the field would not change when you rotate it, or any change that you do see would be due to lack of uniformity in the manufacture of the magnet.
correct.
Well, the B field remains the same, but the flux lines rotate. The B field is not dependent on time. Well, you know, in this case anyway. And if
Well,
you're
you hit upon the point, Dennis. The point is that Faraday's rule, flux rule, says that the field lines moving is what brings the EMF into existence. The EMF, or the electric force, is brought into existence by the field lines moving across the circuit, or the wires of the circuit. Okay, and it turns out that the field line, the rotation of the field lines, really doesn't have any effect on the EMF. It's the motion of the circuit, the physical movement of the circuit, that brings about the EMF. And this is really basically the crux of the problem, that the inability to make the distinction. Now, Faraday said, well, I can make this work if I say the field lines aren't moving, okay? In which case he sort of saves the theory by that hypothesis, which seems non-physical. And that's kind of the essence of what the Faraday paradox is.
And that's why presumably later on he reversed that ad hoc hypothesis of his and actually came to the opposite conclusion. Isn't that so?
I'm not really sure that's true. I didn't read that in Faraday. Now I know other people have, confused on that, but I think Faraday pretty much, he may have made some. I'm not at all familiar with that, so I'll just leave that one alone. Okay.
Okay.
I've never read that, so in Faraday.
He might have been as confused as we all are, though, on the whole subject.
Well, this is, I think, an example of a theory where you try to interpret the data to save your theory. Okay.
Right.
And I think that's what science is doing today. Scientists, when they do experiments, are more interested in making sure their theory is proved correct than investigating, interrogating nature, so to speak. And this is a good example of where people kind of get more involved in proving their theories and don't do very good experimental design. And so they do an experiment and their experiment looks like it confirms their theory. And so they publish a paper saying, yay, my theory is confirmed by these experiments.
Yeah, Harry, you mentioned that you could visualize the rotation of the magnet pole. And I was wondering if you have any references, because I was looking for that on YouTube just now. And I could see some experiments like that, but they were clearly with not just looking at the pole, because I would be surprised. I would think that if you put a viewing filter on just the pole of a rotating magnet, that you would not see anything. So,
well, it says there's the alignment of the ferrofluid. This is, and I put out a video, a paper that refers to this video, Unipolar videos. I don't know if you ever seen that paper. That was put out several years ago. You never read that? That's in there. But basically, it doesn't make any sense that the magnetic field would not rotate with the magnet. So the bottom line, because the bottom line is, if that happens, something seriously wrong. The idea is that Mr. Keene said that you're dealing with a symmetry effect. So the rotation of the magnet doesn't, if you have good symmetry of the cylindrical magnet, the field produced by that magnet, the flux that produces, doesn't change as you rotate the magnet because of symmetry. That's the point. It's not the issue of whether the field lines rotate or not. That's not really the issue. The issue is when you rotate the magnet, does the flux, okay, produced by that magnet change? And if you have symmetry, it doesn't.
That
Well,
would,
it's not the flux that doesn't change, it's the B field that doesn't change. The
Well, they're the
flux
same thing.
refers to the lines of force.
Well, the B field is basically the flux of the magnet.
No, it's just the magnet. It's just the magnetic field strength at that point.
All right. And now we're
measured.
into the misunderstanding of magnetic field versus the magnetic flux.
Yeah, that's right. The flux, I think, to be the lines of force. The
lines of force.
Field, the magnetic field strength at that point.
All right, let's get clear about this. This is the big confusion in the theory. The lines of force are H, electric field strength, and the flux, or the flux density more properly, is the B field. Now, if you integrate the B field using Stokes' theorem, you get the flux across the circuit. The H, which is magnetic field strength, okay, is the lines, the field lines, okay? And B is the flux density, and if you integrate B, you get the total flux. Now, I didn't say the word flux density, I said flux. And what you do is you integrate the B field to get the total flux. The Faraday law says that if the total flux changes, I'm going to get an EMF. Now, I don't know, we resolved the last thing that we were talking about.
Well, I'd like to say one more thing about this. When you rotate a cylindrical magnet that's around the axis of symmetry, the B field or the H field, as long as there's no, you're outside the magnet in a vacuum or something. The B field rotates, the flux lines rotate, but the B field is constant because of the symmetry. But so to measure the fact that the B field is moving, rotating or not, you have to use induced current, whether it's inducing a current or not, in something that's fixed with respect to the inertial system. So just like in the E field, if you rotate a condenser, the E field about the axis of symmetry, the E field doesn't change, but it induces a B field. But by the same token, if it's actually rotating, depending on how fast it's rotating. But
I think the real issue here is that this argument that you're making is really the bone of contention about this whole Faraday paradox. That's the point. And you know, people have different perceptions and different ideas about what they think's going on. And the writers of this particular paper, towards the end, they go into this whole issue about, is the field real? Is it not real? There's all these different opinions about whether the field is a meaningful concept or not a meaningful concept. And so therefore the Weber theory might make more sense because, well, we can make it more physical by this force between current elements, and the current elements are moving, and therefore, we don't need this field idea because it's too unclear and uncertain, ambiguous. And that's kind of really what they're trying to get at. But unfortunately, I don't think their experiments really justify this type of argument.
Yeah, I can't understand the design of the experiments using a bar. Why didn't they use a slab so that when it's rotated, you would expect that the magnetic field outside of the slab would be changing with the rotation?
All right, let me just sort of address this issue. I've been talking. I haven't talked about the experiments that were done, and they were done on a lathe using, and this business of using a lathe to test the Faraday theory was sort of brought into vogue by Kelly, Al Kelly, who you may have heard of, and so what they're doing is they're using ceramic circular flat magnets. They're not long cylinders, they're flat magnets. And so they may, I think they may be like a quarter of an inch or a half an inch. I don't know how thick they are, but anyway, they're discs, they're disc magnets. And so what we were talking about earlier with the cylinder was basically what Weber did, and what people in the early days in the 19th century and maybe earlier in the 20th century, they were using cylindrical magnets. And I'm not sure I really helped you, but that's the reason we were talking about that, because that's kind of the way the original experiments were done that kind of precipitated the controversy. Does that help you any?
Yeah.
It might have been just convenience, because I think they used an old magnet from a loudspeaker, these sort of cylindrical.
Yeah. Yeah, I think some people have done that. The point is there's a slew of experiments that have been done, and I didn't really get into the part where you get into the Einstein theory of relativity. And, this is a really subject that, you could probably talk about for 10 hours maybe and still not really get a good idea of what's going on. That's why I sort of tried to limit it a little bit to an introduction and talk about these particular experiments, because if you don't do that, then you get involved in what everybody has done and all these different experiments and the disagreement between the experimenters and that sort of thing.
Yeah, I don't understand. The design seems to be really lacking using a cylinder. Why not have any sort of a magnet spinning, but off the spin axis, significantly off the spin axis, so that you're really assured that the flux lines in your measuring device with respect to the voltage induced is experiencing a varying magnetic field?
Well, I'm going to answer that by saying that people have tried to do that. Not exactly as you described it, but there are people who have taken these disc magnets and taken a slice out of the magnet so that it's no longer a symmetrical field, and done experiments. And these things are kind of confusing. The reality is that what's happening is, in the particular type of experiment that we're talking about here, is that it's disturbing to people that their theory of the motion of the field lines doesn't enter into the calculation of the EMF that's produced. So the motion of the field lines has nothing to do with the calculation of the EMF. And this presents a problem for people who want to use the Lorentz force law, okay, this V cross B law, because V can't be defined. It's ambiguous. And so that's really what the problem is. And that goes back to Faraday's idea about the lines of force moving. Faraday thought that it was the lines of force, the motion of the lines of force cutting across the wire or the circuit that brought the EMF into existence. And that's kind of, I think, the crux of the misunderstanding. In the case of the spinning magnet, the flux itself, the total amount of flux, doesn't change. When the circuit, it's when the magnet is moving, the magnet or part of the circuit is moving relative to another part of the circuit. That's when you get an EMF. You get an EMF when there's a motion of the circuit or the object in which the EMF is being induced is moving. Okay, it's not the motion of the rotation. It's not the rotational motion of the magnet. That doesn't change the flux. The flux doesn't change because the magnet is rotating.
Well, you can,
Yeah, you're
you
breaking
seem
up.
to be changing your mind. Earlier, you said that you thought that when a cylindrical magnet rotated about its axis of symmetry, the lines of force were moving.
The lines of force, that's not what. No, the argument is that has to do with it's not physical to say, okay, that the lines of force aren't moving when, see, yeah, I understand this is kind of why people get confused. This is where the point of confusion is. The flux and the magnetic lines of force are not the same as the total flux that the magnet is producing. Because of the symmetry, the flux doesn't change when the magnet's rotating. The total amount of flux doesn't change. Okay, but
Well, the magnetic reading at any point is the same. Not a function of time.
if you take if you have a case of symmetry and the magnet is perfectly symmetrical and you rotate it and it's a cylindrical magnet and you have cylindrical symmetry, if you take a flux meter, a measuring device, and you put it in the field of the magnet and you rotate it, that meter is not going to change its amplitude. Does that make
No,
sense?
it's not. But thing with the E field. The E field, if you take two cylindrical, two discs, a two-disc capacitor rotated about the axis of symmetry, the E field doesn't change, but the B field does.
Well, I don't know about that. We're talking about something different now. Okay, let's sort of get back. Okay, getting back to the, so what people tried to do, the issue had to do with where is the EMF. Once you get this idea in your head that the rotating lines of force, okay, so we have two ideas. We have these lines of force, which is Faraday's lines, which is essentially the origin of the field context. They're either rotating or not rotating. That's not really the issue. It's their motion doesn't really produce the EMF. Okay, it's the change in the total flux in the circuit that causes the EMF. Is that so? What people have tried to do is they've sort of said, well, if it's, let's identify where this EMF is being produced in the circuit, which is still based on the hypothesis that it's cutting of the lines of force that causes the EMF. Okay, now that doesn't, and so people have tried to attach the voltmeter to the circuit that's spinning in these experiments, and that doesn't really produce, that doesn't tell you anything. It shows that there's no EMF being generated in the disk, which is kind of a contradiction. So there's no voltage measured when the disk is spinning. So that sort of implies that there's no EMF produced in the disk. All right. And we're going to talk about this a little more. This may be a little confusing to you. So this presents a problem. So one of the aspects of this experiment that they're going to do is they're going to try to prove that there's an EMF being produced in a particular place in the spinning object. And we have a closing wire not shielded. Now, if this closing wire or this object that's when we have the voltmeter attached to the disc and we spin it, it's in the magnetic field. So the argument is that there's an opposing EMF induced in the voltmeter that's spinning along with the disc, and so you can't really measure it. So this is a problem. Where is this EMF coming from? All right, now I'm going to talk a little bit about this experiment. It's published in October. It gives a very long discussion of the bibliography. And so I'm going to go here. Let's see if I can do this. And that was their table of results. Okay, here's the paper. Oh, wait a minute, this is not working. Apparently my computer is slow. All right, here we go.
We had a momentary outage.
Well,
Okay, here it is. Resolving the paradox of unipolar induction. It's in this scientific reports. All right. Here's the spinning magnet, north, south. Here's the disc. Okay, this is the classic. Now, if this voltmeter, as I talked about earlier, if this voltmeter spins with this disc, you get no voltage. Okay, and so they're sort of saying, well, you have to include this part of the circuit in your experiment, and it's sort of puzzling to me why they did this. And, because it's already been done. Why would you repeat an experiment that's already been done?
Your parish, Sherry.
Excuse me?
Publish or perish.
Okay, here's the setup here. You got the magnets, they got a spinning lathe, as I said before. Now, if you go, if you're interested in this, this has been done a lot in recent years, where people have spun these magnets on a lathe. Like I said, I think Al Kelly was the first to do that many years ago. Here's your disc, okay, which they call disc DA. And it's got contacts, sliding contacts. Here are the important sliding contacts. Okay. And then here there's a printed circuit board that's in the shape of a disc, and they have an LED on it. And that's an indicator. Here it shows the setup here. I'm not sure exactly what the camera does. I guess they want to photograph the process. I guess maybe that registers whether the LED is lit or not. Let's go down here. This shows the circuit board. Here's the what they call it. I don't know if you're familiar with what an instrument amplifier is. Instrumentation amplifier. It's a integrated circuit that op-amp type circuit. Here it is here on this circuit. I think there's another. So what they're doing is they're attaching via these contacts. Okay, they're allowing the disc. So this voltmeter circuit is going to measure when the lathe is spinning, it's going to try to measure the, here it is measuring the potential between the rim of the disc and sort of midway from the center, a little bit from the center. So should be an EMF induced along this point of the disc. So they're going to measure this, and then when there's a voltage, this LED lights up. Does anybody have any questions about this?
So the circuit board with the LED on it is not spinning, Harry?
It can spin or not spin. That's the whole point. Okay, so they have, here's their, they make predictions. And here we have the issue of the omega. That's tells you whether the disk is moving or not. So DA is the disk that's spinning next to the magnets. BC is the measuring device. And then here we have mega means it's spinning or not spinning. Okay, and then here we have the state of motion of the magnet. And one of the things that's curious is, oops, here are the predictions. All the predictions are the same. Why would you do an experiment where all the predictions for your different theories produce the same results?
Well, because you have to publish or perish, and you've got higher technology, so you can justify it by saying that your results are more accurate.
Well, here's my thesis, and I'll give you my thesis. My thesis is that they want to demonstrate that the Weber theory is as good as these other theories. So they're kind of bringing the Weber theory in and saying, well, when we did these experiments, the Weber theory, gives the same, is acceptable. It matches the experimental results. And then in their conclusion sections, when they talk about the field, they sort of badmouth the whole idea of the field, and they point out this contradiction between whether the field is moving or not moving. That sort of disqualifies that theory, and so that sort of tends to elevate the Weber theory.
So in a word, Harry, could you say in regard to this particular experiment what the Weber theory is? I mean, each stationary field is clear, moving field is clear, but what are we talking about here? The velocity of charges?
Yes. Now, I have to apologize here. I'm not a proponent of the Weber theory. The Weber theory, in my mind, is sort of, it says that there is a force between current elements. And so what they're going to try to do is they're going to say if this current element is in motion, okay, the Weber theory makes predictions about moving current elements and that sort of thing. There's a Weber force law, and proponents of the Weber theory, they're sort of trying to bring this theory into contention versus the accepted Maxwellian theory. And I don't think this really basically does a very good job of doing that. That's kind of my point. Does that answer your question, Ian?
Well, somewhat. Presumably in regard to that, Harry, the two first columns, the SF and the MF, are actually by the Maxwellian theory. So in a way, they're contrasting that with the Weber theory. They're getting the same result.
I'd call it the Faraday Maxwell theory with the emphasis on Faraday.
Okay.
Because that theory, the Maxwell theory sort of follows Faraday in the hypothesis that there's this field, and it's the field that creates that is doing things. So the Faraday is according to the historians the originator of the field theory, and Maxwell basically read Faraday's experiments and then developed his theory based on on Faraday. But when you look at his treatise, you'll find out that he brought in all of the other people too. He brought in Ampere and gave a nod to him, and pretty much all of the people who had done work in electromagnetism were sort of accepted into the Maxwellian fold, so to speak. But I think they've sort of, the modern theory is sort of amalgam of all these different concepts. The Amperian theory, Weber, now remember, Weber is a little later than Faraday. Weber's theory is an action at a distance theory. It's more like Newton's gravitational theory, where a current, or Ampere's theory, which is that there's a force between current elements. And Weber adds in the what if the current elements are moving?
Yeah, Weber, if I might real quick, Weber took Ampere's results and these current elements and kind of developed it into, well, what if these current elements consists of a positive charge and a negative charge, and those are in motion. So Weber goes from the current element idea to individual charge particle idea. And now you're at a fundamental, a charged particle is interacting with another charged particle, and they can be moving relative to one another. And that's Faraday's force, Weber's force equation.
Right.
It's just the relative motion of charged bodies with respect to each other.
Right. Now, yeah, Weber has positive and negative electricity, and they're moving. Okay.
Weber's theory, according to Wesley, works really well, except for when radiation is involved. His theory does not.
I don't think it works at all in this particular problem. Although, and that's kind of gets to the point of my point that I'm trying to make here. I'm sorry, this is
Danny, your sound is breaking up again.
Wesley developed his.
Now, my point is, I don't think that Weber theory, I don't think it works here in this particular, and I think it's part of the point of what they've done here is they've tried to make it look like Weber's theory. But here's shows the disk and the amplifier connections, and they try to explain why the when the light lights up and it doesn't light up. Okay, so here we're at the results, and
do they conclude from this, Harry, anything with regard to the seat of the EMF? You know, if it's in the magnet or the disk or the circuit?
Well, I talked about that earlier, and the whole, I don't think there's a seat of the EMF. That's kind of really the issue. My view is, and I'll talk a little bit about my theory or my idea about it, is that there's no quote seat. It's the entire circuit. So it's the flux changing in the complete circuit. And when you try to say, you can say that a particular part of the circuit is moving in the magnetic field, okay? And that's pretty easy to do. So you could say that's the seat of the EMF, if that's what you mean by that. But it's the total flux in change in through the circuit as a whole. That's Faraday's law. And the argument is, is this law valid or not? And I think what they're trying to do here is they're sort of trying to say that, well, Faraday's law really isn't valid. We should be using the Weber theory instead. And Weber's theory explains these experiments. So Weber's theory is okay. But I don't think these experiments really test the actual paradoxical situation.
You see,
Yeah,
Kelly mentions, Denny, that Wesley in 1991 stated that the EMF remains in the disk when they're co-rotated, but he contends that that is not true, and he basically he says that a voltage is generated between 2 points on the periphery of a magnet, one of which is closer to the midpoint of the magnet. And this voltage was not picked up in Muller's experiments, but he claims that's because Muller was using ceramic materials, which wouldn't be conductive. So he says, because we record a voltage, how can the seat of the EMF be in the disk, which does not exist in this case? He claims.
Well, I'm not really familiar with this. I don't believe that this issue about where the EMF is being generated is. That sort of, to me, is harking back to the whole lines of force crossing, cutting the flux cutting hypothesis, that the lines of force cutting across the circuit or the wire induces an EMF in the wire. So that's saying phenomenologically that it's the movement of the lines of force that produces the EMF. But I don't think there's any evidence in any of the experiments that that's the case at all.
I'm confused with the terminology EMF in this setting. I understand it from the physics textbooks, but to me, EMF here would be a force on the conductive electrons, or the force on the charged bodies would then redistribute the conductive electrons. And once they're redistributed, now you got a voltage between two different points. So it's really what is the seat of EMF is what is causing the force on the conductive bodies.
There isn't any, that's the point. That can't be determined.
Well, I'd go back and say it's the other charged bodies, the charged bodies of the quote unquote source acting on the charged bodies of your detector.
Yeah, but the experiments don't.
They don't distinguish. Yeah, the experiments are not distinguished.
Don't allow you to actually make that determination. That's kind of the whole point.
Well, if there is an EMF, then there has to be a force on those charged bodies to redistribute those charged bodies.
If you believe in that theory.
Okay.
So,
I'll go with that. Yeah.
So the point is, you really sort of stated the Faraday paradox differently. If you believe that the Faraday, I didn't say that Faraday said what you said. Okay, that there's a force acting on the electrons inside the wires. Okay, because Faraday didn't know that there were electrons, and he didn't have that concept.
Right.
So the modern idea was they would translate what Faraday was trying to say into the modern idea that the lines of force, the motion of the lines of force of the magnetic field moving across the circuit element creates this Lorentz force V cross B, right? And which is a force acting on electrons inside the wires. So you would say, okay, that explains it. That creates the EMF. And that can only occur where there's a magnetic field and you have motion of the circuit relative to the magnetic field. But the experiments aren't consistent with that. They say that when there's a relative motion of the circuit in the magnetic field, there's still an EMF being created. There's no EMF created in one case, and there is an EMF created when there ought not to be. So when there's no motion of the magnetic field, there's an EMF created, and when there is motion of the magnetic field, EMF is not created. So you can, in these experiments, you can produce these two instances that contradict each other. And that's where this hypothesis of is the field rotating or not rotating enters into the controversy. Did I help you? It's kind of hard.
Oh, sure.
It's
Thanks,
hard.
Harry.
Well, the problem seems to be the Lorentz law of force. When we when I gave my last talk, I mentioned that the Granows,
Right.
had shown that the Lorentz law of force did not explain up to a multiplicative factor of 2,000 the forces on the Ampere pendulum that they developed from the Ampere.
Okay, so we got a little off topic here. Anyway, my point, here's the point. The point is that when you look at these results, okay, let's looking at the table. Can everybody see the table?
Yes.
Yeah.
Over here, they have what's called NP and IP for CW rotation and clockwise rotation, NP and IP, and then you have these ones and zeros. Okay, that means that they lit up. Okay, so let's start off with case one. There are eight cases, and that's 2 to the 3. And so you have 3 things that you're moving: DA, which is the disk that you're it's exposed to a magnetic field. You remember the lathe. Then there's BC, which is the measuring device, the circuit board, and then there's the magnet. And so case one is all of them are at rest, and you measure nothing over here. There's no 0, 0, 0. There's no voltage. The lamp doesn't light up when all 3 are at rest. Well, you wouldn't expect there to be. Case 2 is now the disk is rotating and the measurement circuit is not rotating, and we get an EMF. And they do this in the I'm assuming that they mean both. Well, okay. In this case, the DA is rotating counterclockwise. We get a voltage, and when DA is rotating counterclockwise, we get a voltage in the negative direction. That's kind of confusing because this complicates the table. All right. Now, what's interesting is that when you do the counter, this is a lot of symmetry. There's a lot of symmetry in these experiments. And really, what you want to do is you want to figure out what are the symmetries. And that's what makes this table useful. And unfortunately, they should have put a 1 in here for omega rather than omega. And so you get 0 is false and 1 is true, or you could, if you look at it that way. So 1 being yes, true, we get an EMF. 0.
Sorry, are we looking at the same table, Harry? Because the one you have up here seems to have not 1s and 0s and omega. It has V and 0s and plus. Table 1.
Yes.
Well, I guess I'm sharing the wrong screen then.
Okay. Right. Thank you.
This is and zeros and omega.
Yes.
Okay. And NP, IP, NP, IP, counterclockwise, clockwise. Okay. So what we have here is symmetry. Now, notice, and just going over this, you don't get an EMF when DA and DC rotate together. You see this? When they're rotating together, you get nothing. You only get an EMF when their rotational state is different. You only get an EMF when they're different. When the rotation of, and guess what? It doesn't matter what the magnet is doing. Whether the magnet is rotating or not rotating doesn't affect. So you could take this magnet out of the table. It's irrelevant. It's a don't care truth state. You know, in your truth table, has nothing to do with what the result that you get is same and different. When DA and BC are rotating the same, you get nothing. They have to be different. So that says that there has to be a difference in the circuit, the complete total circuit that includes the measuring device and the disc that's spinning. There has to be a difference of motion of those two parts of the circuit in order for you to get an EMF produced. And the magnet has nothing to do with it. Whether the field is rotating or not rotating has nothing to do with the result. And that's really
What about when there is no magnet?
you get nothing. Doesn't matter whether there has to be a magnetic field present. So it's whether the magnet is rotating or not rotating. The motion of the magnet doesn't change anything. And this goes back to what we were saying. Huh?
Understood.
So the flux isn't changing when you rotate this magnet. What changes the flux is the difference in motion between DA and BC. So this says that it's the circuit motion and it's the velocity of DA moving with respect to BC that changes the amplitude of the voltage. It's not anything to do with the velocity of the magnet. You can change the velocity of the magnet to whatever you want, and it will have no effect on the voltage that's measured. The voltage that's measured is changed by the velocity, the relative velocity of these two parts of the circuit. So it's the relative motion of the circuit itself. So the difference in the velocity of different parts of the circuit that causes the EMF.
That's certainly a point taken. But I mean, according to the theory that the rotation of the magnet is causing opposing effects in the disk and the external circuit, which cancel out. That would explain why the motion of the magnet is irrelevant once the magnetic field is there. Now, the other experiments which have been done with regard to shielding that you mentioned earlier seem to have employed like a soft iron yoke to indicate that even when it was the external circuit was shielded, it made no difference. But one might question the efficacy of that shielding.
Well, the real issue here is, as I've tried to explain, I'm going to try to explain it again. The magnet moving, rotating, doesn't change the flux that's produced by the magnet. So the magnet flux, the flux produced by the magnet is not changing. So that indicates that it's the magnet flux doesn't change. It's the same. Whether it's rotating or not rotating, the magnet flux stays the same. What changes the flux is the relative motion of the circuit elements.
Yeah. Well, it's just that if you're talking about relative motion, I mean, a motion of the magnet against a stationary disk or circuit should be the same as a rotation of the disk or circuit against the magnet. The same principle should apply. that you mentioned?
Well, I'm not sure what you're saying. That it doesn't really matter. What really matters is whether these BA and BC are moving, whether or not they have the same motion or different motion. And if they have the same, if they're both spinning, you get nothing. If they're both at rest, you get nothing. You only get something when they're moving in different states of motion.
But if one of them is taken out of the equation and the magnet moves, you will get an EMF, notwithstanding, the discussion earlier about the symmetry of the magnet and having no net effect on the B field.
Well, yeah, this is why this is kind of these experiments that they're doing here, that they've done here, they're not really as complete as you would like. Mueller has done a more complete set of experiments, and if you want, I can talk about that a little bit. Let's see here.
And Wesley talks about these experiments in his
Right.
Scientific Physics, Chapter 5, which I've discussed with Denny in the past. So,
All right, and he talks about 4 cases: A, B, C, D, and C and D. This wire ECR is shielded, presumably because the flux is diverted away from the wire, so it doesn't intercept this wire here. And you see here it doesn't intercept the wire. And then here you have case A, and then okay, so these are the A and C. The magnet is rotating around its axis, and in B and C it's moving laterally. So this is the interesting thing. The experiments that they did agree with A and B. So if you look at the truth table up here, okay, whether you get an EMF or not, A and B are the same. And that happens when the parts of the circuit, IR and ECR, are moving differently. So when they're the same, no voltage. When they're different, you get a voltage. Different, you get a voltage. Same, you get no voltage. That's the same results as, so in other words, all they did was just repeat Mueller's experiments using a different apparatus. So they didn't really add anything, any real new information. They just repeated what Mueller had already done. A and B are the same, and it's C and D that you get that you have to explain. So these experiments don't really, that were done, this experiment where they claim that we're resolving Faraday's paradox, they didn't really resolve anything at all. They just repeated what Mueller had done, and basically confirmed his experiments. So we're kind of back to where we were before.
In the previous table, the clockwise and counterclockwise results were different. Not that one, the one before that. I guess you called it the Mueller.
I'd have to go back. So go ask your question.
Why would the clockwise and counterclockwise for the NP results be different?
Well, because the voltage, the EMF is reversed when you reverse the direction of motion clockwise and counterclockwise, if the polarity of the magnet stays the same.
But presumably there would be a voltage, but the table, yeah, that table there shows, for example, on row 2, with the counterclockwise, you get a voltage, but with the clockwise, you don't get a voltage. Why don't you get a voltage? It should be
the measuring device is polarized.
Okay, all right. You've got a
So
diode.
the measuring device only, that's, if you had a voltmeter that allowed you to measure plus and minus voltages, you could, instead of having a 1 here, you'd have a -1 or a +1. But this device, this operational amplifier, only lights the lamp. So what they're doing is, when you get a
Right, there's a
positive
diode.
voltage
Okay.
at the amplifier, it lights the lamp. And if you get a negative voltage, the lamp doesn't light. And so,
Got you. Okay,
is that,
yes.
this is kind of, this is sort of, it would have been better if they'd simplified this table by not doing, I don't really, this was done by a graduate student apparently, and he did a pretty good job of the history part and surveying the literature, but in designing his experiment, he didn't really, it really didn't do anything to really resolve any of the issues. It doesn't resolve the paradox. It just adds another set of experiments that people can, in a paper that people can read and get confused, because it's what people have done in the last 20 years have been essentially promoting Weber's theory, okay, as an alternative. And that, in my mind, that doesn't really help to resolve the problem, because it just gives another theory that you have to figure out how to eliminate from contention, when you already had confusion existing when you were using the Maxwellian or the traditional theory. So the traditional theory couldn't explain very well what was going on. And bringing in Weber's theory didn't really help to resolve anything. It just made it more complicated and created more controversy.
Yeah, I'm not quite sure how Weber's theory, so Weber's theory is that there are no magnetic fields, that everything is caused by the electrical circuits. So I don't.
Weber's theory is that charges interact, that the charge elements, David explained it a little better than me, that essentially the charges in flowing in the circuit, okay, you can, I guess I have to call on David to explain it again. He did a pretty good job of explaining it previously. There's plus and minus electrical charge. There's what's called the electrical fluid, and I'm not really sure exactly how they deal with the plus and minus electricity.
Yeah, I would think if they're doing a Weber thing, they would have used an electromagnet rather than I don't know, a permanent magnet. Certainly
Well,
the two circuits in that case.
my problem here, I'm going to be quite blunt about this. My problem is where is this current inside of a magnet? Where is the current inside of a permanent magnet?
Yeah, I would think that there would have to be like a superconducting current inside a permanent magnet for it to do what it's doing.
Well, what they do
Well,
is
it's just that the electrons can be viewed as a torus, a donut, if you like, of charge rotating, and these magnetic fields are either lined up or not. If they are lined up, then you have a permanent, you have a magnet, and if it's permanent, they're permanently lined up, you have a permanent magnet.
Yeah, but I don't want to get into like how permanent magnets work. That could be the entire talk by itself.
Well, I can't help you there, Franklin. What they're hypothesizing is that there is essentially you have what's called an ampere current, an Amperian current, which is a fictitious current that's equivalent to the magnetic field of the magnet.
Yeah.
Who's this David, Harry, that you were referring to? That is
David Bauer. Is he here?
Oh, David Bauer. Yeah, okay.
Although you did mention that, this particular experiment would be the voltmeter attached to the disk kind of thing, because the voltmeter is immersed in the magnetic field at all times in this particular experiment, right? That's the deal.
Yes.
So
It's, they're a little bit unclear about that, but let me go.
yeah, based on the picture, it's like the magnet and the disc, the circuit and the disc are very close to each other. So it's quite clear that the magnetic field.
Now here it is. Here's the picture. Uh-oh.
You
Did it
did
go
mention,
away?
you did mention in that particular case that the opposing EMF would be generated in
Here it
the
is.
circuit. So doesn't
Here it
that
is. Here's the magnetic field, and you see the meter here is inside the magnetic field. They don't tell you what the polarity of the magnetic field is, which I don't particularly care for. This is all very schematic. It's kind of vague.
Yeah, but I would agree with the, you mentioned that, well, in that case, then the meter would be generating an opposing EMF to the one that's in the disk, maybe essentially going in the same direction. So of course
That's
meter is going
now
to
here again, you're jumping to a conclusion. Okay, according to the theory of the theory that V cross B theory, the Lorentz force theory. According to that theory, there is a reverse EMF in this part of the circuit. You see where I'm moving? Okay, that opposes the EMF that's produced in this part of the circuit, and the net result is 0, and so therefore the voltmeter doesn't move. They explain this up here a little bit. They don't explain, they talk about whether, so if you have an EMF induced in the opposite direction to the EMF that's produced in this direction, then you'll get a 0. You won't get this device will not detect a result. Now, this sort of is a flaw in the experimental approach.
Well, I wouldn't get that. I would think that if the circuit is immersed in the same field as the disk, and it's rotating with it, that the arrow would be, say, on the left-hand side, would be down on both sides. There wouldn't be a loop. There'd just be. I don't understand what these diagrams are trying to show us here, because
they're talking about this. This is the current is flowing through the device. Okay, these arrows are current direction arrows.
yeah, and that can only happen if the circuit is stationary.
Well, I suggest that you read this is not really very well explained, and it's kind of confusing. A lot of the papers, and I think this is one of the problems with the work that's being done in this area, and that is that the people who are doing this work aren't particularly articulate, and this particular paper, which looks to be, he does a pretty good job of, if you're going to go down here to the
Well, it's just I'm not
bibliography, excuse me, the bibliography is very thorough. Okay, and but it's not real clear to me that he really read them all. I think he just looked up all these references, and then he gives a very good introduction where he talks about the history of the paradox and what's been done. But when it comes to explicating his experiment, it's really not done very well, and it's kind of confusing what he did. So I suggest that you read the paper if you're interested in finding out more about it.
Well, like you said, I mean, your point was they did this experiment, which has already been done, and came up with the same results, and still not explain anything, right?
Well, they're saying that Ampere's theory satisfies the experimental results, and so if you read between the lines, then they're sort of implying that that the Weber theory is the answer.
Yeah, I don't think that's the answer. I mean, I think the crux of the paradox is that if you have a magnet and it's rotating, the way the magnetic field lines are currently defined comes out from the poles, and so you'd think you'd be able to see those lines rotating. But as you point out, what those magnetic field lines are really saying are just regions of equal potential, and that's just one way to describe equal potential. With going from north to south, because you could describe equal potential as being rings around, rings around your magnet. That would also be regions of equal potential. And obviously, if you spun your magnet and you were looking at the equal potential as rings, then you wouldn't see that moving at all. I mean, I think that's actually the source of the paradox, because the way that you graph the field line, you can graph it from pole to pole, and that represents an equal potential line from pole to pole, or you could represent the equal potentials as concentric rings. And in one,
Yes, that's right. The concentric rings, are the A field, and the other ones are the B field. The consecutive rings are the A field.
Yeah, I mean, either of those, either like A or H, those are both valid descriptions of what you mentioned as the actual flux. If I take a Hall sensor, magnetic Hall sensor on that rotating magnet, it's not going to measure any different. It's going to see the same thing, right? And that's I think the ultimate solution, which is that you're looking at.
Why don't you write a paper about this and submit it to us? Essentially, these EMF is produced by a change in the flux. It's not about the magnetic field lines.
So Harry, we just got a warning that we've 10 minutes left. Would you like to spend a minute or two summarizing the whole proceedings, and then I'll close the meeting in an orderly way, rather than just be cut off? It's always quite disconcerting if that happens.
Well, all right, I'll try to summarize this as best I can. This paper here, Resolving the Paradox of Unipolar Induction, New Experimental Evidence. Well, we can't really say that it's new experimental evidence, which they're claiming doesn't really appear to be new experimental evidence. And it doesn't really appear to resolve the paradox of unipolar induction. So that's kind of disappointing that we don't get a resolution of the paradox.
So is that all you want to say? Because what I was going to say is, well, it's been an extremely interesting session, but rather alarming in that, well, it's refreshing that for a change, you're not pushing one theory and saying, oh, we've now solved everything and this is the answer and everything else is wrong. But on the other hand, you've come to a conclusion that despite all the myriad of experiments that have been done over the last 170 years, including the most recent experiments here, it's still a paradox. No simple explanation can be proffered. And indeed, I think—
Excuse me, Ian. I don't think there's a paradox. I think it's the paradox is a result of confusion.
Well, call it what you will, but aren't you basically saying that you're questioning the whole procedure, the whole scientific procedure in trying to resolve this and explain, all the 8 different possibilities in the table? And one can partially explain one bit, but then one gets into difficulties with regard to the other. One can start talking about the field moving. One can start talking about the influence of the external circuit. But there's always—
All right, let me sort of summarize a little bit about what the issue is. The issue is it's kind of complicated. Faraday, I think, made a mistake when he started talking about the flux cutting rule. that the lines of force created the movement of the lines of force created the EMF. So that's kind of what Faraday was saying. And he could, when he did this, got to these experiments with the magnet rotating, he couldn't really bring those into to be consistent with his theory of that the cutting of the lines of force moving caused the EMF. Okay, that's really kind of what the paradox is that he made, and that's a problem of the theory. But the modern theory says that it's the change in the flux that produces the EMF. It's the change in the total flux across the circuit. And that theory doesn't seem to be disproved by any of these experiments. So it seems to be an argument about what theory is correct when the theory that they have works. It's just that they're doing experiments that don't appear to bear it out in the experiments that they're doing. So people who want to promote other theories or different theories or find mistakes or errors are producing these experiments that are creating more confusion.
Might be interesting to know what experiments or experimental design might in fact distinguish among these three theories, or perhaps even exclude them all.
Well, the point is that
Al Kelly's book, Challenging Modern Physics, which I can show here on the camera,
Yeah, I have it.
has chapter 9, an entire chapter devoted to unipolar induction, which Ian told me about. That might be an interesting talk sometime in the future.
well, to get back to the bottom line, Mueller has done these experiments, and he's proposed a theory, and I think it's probably, and I think I had his, he produced a recent paper, Francisco Mueller, I think is his name, and he refers to something called the edge effect. And it's kind of hard to understand what he's talking about. The issue here isn't really doing an experiment. That's not really the issue. There's lots of experiments that have been done. The issue is trying to get people to agree on what the experimental results imply as far as a theory being correct or incorrect.
So, in summary, Harry, would it be fair to say that you are suggesting that it is not necessary to do any more experiments because all the experiments have been done, because we're just
Correct.
repeating? Yeah.
Right. The issue is getting some agreement on what the experiments that have been done demonstrate as to what is a true correct theory or not a correct theory. And that seems to be the issue. Some people maintain that Faraday's law is not violated by any of the experiments. And there are other people who sort of want to maintain that, yes, Faraday's law is violated by the experiments. And if you get rid of Faraday's law, then you've sort of basically ripped out the underpinnings of Maxwell's equations, which might not be very good.
Well, you know, to say a few closing words, really, I'd like to thank all of you for participating today and contributing quite in detail to Harry's very clear exposition of this problem, whatever you wish to call it. I think it's something that we'll probably have to revert to again. We have had meetings actually on this subject before, but hardly as deep in such a short period of time.
Thanks, Harry, and thanks to everyone for joining in.